Okay, so the second problem, problem 5.2, wants us to calculate current through R1, current through R2. Okay, so current through R1. If we look at our circuit here, can you guys see this? Well, assuming you guys can see this. Frank?
I mean, yeah, I can see. I mean, it's kind of small, but I mean, I have mine pulled up anyway, so I'm just looking at mine.
Okay, I can zoom with this guy here. Let me see here.
Yeah, I just got mine on my iPad zoomed in, so.
Okay, I just zoomed in a lot more.
There you go. That's a lot better.
Okay, cool. All right, so now, so the first thing is asking us for is the current through R1, right? So let's take a look at this. We know we start out with 300 milliamps here, okay? And a certain amount goes through R1, okay? And then the rest goes through R2 and R3. And we also notice we got 200 milliamps coming back from R2 and R3. So if 200 milliamps are coming this way, and we know we have 300 total, the current through R1 must be 100 milliamps.
100, yeah.
Yeah, okay. So now, the next thing we want to know is what is the value for R1? Well, we know the current through R1 is 100 milliamps, and we also know the voltage across R1 is 100 volts, right? Because if the voltage across R3 is 100 volts, and since it's in parallel with R2 and R1, then the voltage across R1 must be 100 volts.
Yep.
So if you got 100 volts divided by 100 milliamps, you should get about 10K, maybe? Yeah, 1K, 1,000 ohms. Everybody get that?
Now, what does it ask you for the value of it?
I'm sorry?
What does it ask for the value?
Right here. It says for a circuit in 538, compute the following. IR1, R1, current through R2, and GT.
Oh, GT, okay.
Yeah, and we're not going to work with G, unless you guys wanted to. So the next question says, find the current through R2. Okay, so we start out with 300 milliamps. 100 milliamps went through R1, so we had 200 milliamps coming into this node here. If 50 milliamps went this way through R3, how many milliamps must have gone through R2?
150?
Exactly, 150. And then that 150 through R2 meets back up with the 50 through R3, and that equals 200 here. And meet up with the 100 through R1, and that's where you get your total of 300 again.
Yeah.
Everybody cool with that one? Okay, the next one was number 3. All right. Let's see here. I think I can move this. There we go. So number 3 says, for the circuit in figure 539, compute the following. Voltage across R3, current through R1, and voltage across R1. Ah, this would be a fun one. Ah. I haven't done these before. These look like good homework problems. Okay, voltage across R3. Let's see what we know. All right, we know, this one's easy. We know the voltage across R2 is 60 volts, right? And R2 is in parallel with R3 and R4. So the voltage across R3 and R4 has to equal the voltage drop across R2. So if this is 60 volts, and if R4 is 40 volts, what is the voltage across R3?
0.
How about 20?
Oh.
Because the voltage across R3 and R4.
Oh, yes. 40 and 20, 60, yeah, those are.
Yeah, they have to add up to the voltage across R2, right?
Across R2, yep, exactly.
Okay, so that'll be 20 volts on this guy, R3. So now they want to know the current through R1. Okay, the current through R1, that's going to be our total current. So we can figure out that a couple different ways, right? The current through R1 is going to be the current through R2 plus the current through R3, right? Everybody see that?
Mm-hmm.
So we can figure out the current through R2. So the current through R2 is basically 60 volts divided by 1,000 ohms. Which gives us 60 milliamps, right? 60 milliamps through R2. And we just figured out that R3 has 20 volts across it, right?
Yeah.
So if we take 20 volts and divide it by 500 ohms, that will give us the current through R3, right?
Which is 40 milliamps.
Okay, 40 milliamps. Therefore, the current through R1 must be 100 milliamps, right? It'll be the 60 plus the 40. Remember Kirchhoff's current law, the sum of currents entering and exiting a node have to equal 0. So if we have 40 coming out this way, 60 coming out this way and 40 coming out this way, what went in had to have been 100, and all the current goes through R1. So current through R1 is 100 milliamps.
So the current going through R3 and R4 is the same.
Exactly.
40 milliamps?
Exactly. Since R3 and R4 in series, they have the same current.
They have the same current. Gotcha.
Yeah. Okay, so now they want to know the voltage drop across R1. Okay, this is another easy one. Kirchhoff's voltage law says the sum of voltage around a loop has to equal 0. So let's take this loop here. If you have 100 volts here and R2 is 60 volts, what does R1 have to be? 40 volts. 100 minus 60. These two guys,
40.
have to add up to the source voltage. So voltage across R1 is 40 volts.
Yeah, because you don't have to worry about R3 and R4, right?
Exactly. Because the voltage across R3 and R4 is going to be the same as across R2.
Mm-hmm.
I mean, you could have worked your Kirchhoff voltage law. I mean, it says the sum of the voltages in a loop have to equal 0. So you say, okay, the voltage across the source voltage minus R1 has to equal the voltage drop across R3 and R4. And we know R3 is 20 volts, R4 is 40 volts, so that's 60 volts. So 100 minus 60 has equal 40 again.
40.
So you could have used this loop or this loop. Either way, it should give you the same answer. Because the voltage drop across R2 is going to be the same as the voltage drop across R3 and R4 together.
Yeah, 40 and 20.
Yep. Okay, the next problem was number 4. Okay. It says if
The reference said, so what is a G?
Oh, G. Yeah. Basically, G equals 1 over resistance. So whatever our we talked. It was a G in question 5 too. So you basically figure out your total resistance and take the reciprocal of it, and that's G. But to be perfectly honest with you, I've never used G for anything. So I wasn't planning on talking about G.
We won't need that for the test.
No, you won't need that for anything to do with electric metering. There are no G's in metering. Okay. Now, question 5.4 says that if total current in figure 3.8 is changed to 280 milliamps, what is the value of R1 and total power? Okay, so now IT is 280 milliamps. Okay, so let's figure that out. so let's see it again. Let me write this down. IT equals 280 milliamps. R1 is what? Okay, so if we have 280 milliamps total current, right? Some of it is going to go this way and some's going this way. So we know based on the fact, let me see, can we even do this? Figure 330. Oh, I'm on a wrong problem. Ha! I mean, it should be 538. I should be using this guy. Okay, got it. So in this case, if the total current is changed from 300 milliamps to 200 milliamps, what is the value of R1? Okay, so let's see, how the heck can we do this? So if we just change the total current, okay, yeah. So I'm assuming the only thing we're changing is the 300. So if the 300 goes down to 280, we still have 50 going this way and still have 200 going this way, which means R2 will still get 150. So at that point, R1 is only going to see 80 milliamps instead of the usual 100, right? Everybody see that?
Mm-hmm.
So now R1 is going to see 80 milliamps instead of 100 milliamps. But the voltage across R1 is still going to be 100 volts. So if you have 100 volts divided by 80 milliamps, the value of R1 is going to go to 1.25 K. Remember before it was 1 K. Okay, so everybody see that?
Mm-hmm.
Okay, and it says, what's going to happen to total power? Well, total power is going to be our total current times our total voltage. So before, our total voltage was 100 and we had 300 milliamps. So reduce our total current to 280 milliamps, then our power is going to be reduced accordingly. So instead of 100 times 300 milliamps, before we had 30 watts, now we have 28 watts. Yeah, so our total power would it'll go from 30 watts down to 28 watts. You guys getting this? Oh yeah, Gomez got some. Yeah, okay. Yeah, I got it. I wasn't watching the screen. You got it? Cool. All right, Jeffrey, good job. So A would be 280, yeah. Okay, so the next problem, number 6, says change the voltage in R2 in figure 539 to 80 volts, then determine R1 total resistance and total power. So this is 39. So this is this circuit here. Okay, so now in this circuit, we're going to change R2 to 80 volts. Okay, so R2 is now 80 volts.
60.
Yes, R2 is going to go from 60 to 80 volts. That's VR2. Okay. Okay, now determine the value for R1. Okay, so now, if this is now 80 volts, how much current is going through R2? That'd be 80 volts divided by 100 ohms, 1,000 ohms.
1,000 ohms, yeah.
That's 80 milliamps. So IR2 is 80 milliamps. Okay, so now, also, if the voltage across R2 is 80 volts now, then the voltage across R3 and R4 have to add up to 80 volts, right? So we also already know that R4 drops 40 volts, which means R3 needs to be dropping 40 volts too, to add up to the 80. Okay, so let's figure out the current through R3, which would be 40 volts divided by 500 ohms, right?
Yeah, 80 milliamps.
Okay, so IR3 is 80 milliamps. Okay, so we have a total current, or the current through R1 is 80 milliamps. 160 milliamps, right? IR1 is 160 milliamps. Everybody see that?
$160 milliamps?
Yep, 160 milliamps through R1. Now, let's find the value of R1. Okay, we know the current through it. Now, what is the voltage dropped across R1 at this point? If we have 80 across R2, then R1 must be 20, right? Because 20 and 80 will equal 100. Or we could say this one is 40, this one's 40. We got 100, so it has to equal 20. So the voltage across R1, VR1, is 20 volts.